Hello and welcome to today's lecture. So, yesterday in last day's lecture we had discussed about one or two-tailed test of hypothesis, right. So, in a two-tailed test of hypothesis, okay, depending on your confidence interval alpha, so you determine this value of z, which is alpha z alpha by 2, this area under the curve is alpha by 2, this is alpha by 2, okay, and accordingly you accept. So, this is the acceptance region for H naught, whatever is your null hypothesis. Let us say your H naught is mu equal to mu naught. So, then this value becomes 0 after you normalize for a standard normal variable, okay. And your alternative hypothesis H A is mu naught equal to mu naught. So, that is why you consider both the tails, the left tail and the right tail, and that is why it is called a two-tailed test of hypothesis. Okay. So, if your z value for your test statistics, let us say x bar minus mu by s by root n is greater than z of alpha by 2, or z is less than minus z alpha by 2. Okay. So, you know that your test of your H naught can be rejected, otherwise you cannot reject H naught. Okay. And for a single tailed test of hypothesis, okay, for a single tailed test of hypothesis, you are interested in knowing, okay, whether your mu, so your H naught is mu equal to mu naught, and alternative hypothesis is mu is greater than mu naught. Okay. So, you want to know whether this value is greater than the confidence limit. So, if your test statistic is greater than z alpha, so then you will reject your hypothesis and you can accept your alternate hypothesis. Now, alpha corresponds to the confidence level. Okay. You can have alpha equal to, for 5% confidence level, you have alpha equal to 0.25, for 1% confidence, 99% confidence level, you choose alpha equal to 0.01, so on and so forth. Now, yesterday, while testing of hypothesis, we discussed the possibility of two types of errors which can come up. Okay. You have a type 1 error, okay, is the probability of rejecting H naught when it is true, and this is nothing but this alpha, okay, and this you prescribe. However, you can have another type of error or type 2 error, which is the probability of accepting H naught when it is false. Okay. So, if I draw let us say this is your H naught equal to true, okay. This is your mean and this corresponds to mu of 0. Okay. So, you have for a two-tailed test of hypothesis, you have this is your alpha by 2, this is your alpha by 2. Okay. Now, let us say your sample gives you a mean of mu a, which is different. Okay. So, then the distribution say you get. So, this is your alternative hypothesis, which is mu equal to mu a, okay, which is distinct than mu naught. Okay. So, what you see is this area, okay, this area in this part of the curve, okay, this you call as beta, and this is what your probability of accepting H naught when it is false. Okay. So, how do you calculate it? How do you calculate beta? So, for your H naught, you calculate z of alpha by 2 minus z of alpha by 2 and z of alpha by 2, and you know what is the range, okay, what is the confidence interval. Okay. Corresponding to these values of z, for your you have to calculate z prime. So, let us say this corresponds to mu of a. So, you have to calculate z prime using these values of z of alpha by 2. Okay. Using these values of z of alpha by 2, you will get z prime for this value 1 and z prime of 2, and using this you can calculate what is this area under the curve, which is your beta. Okay. So, what you can clearly see from the way we have drawn this, okay, if this curve shifts to the left, okay, then your beta decreases. Okay. For the same value of alpha, your beta decreases if this curve shifts to the left. How will this curve shift to the left? If you increase your sample size, which means that your deviation of this population keeps on decreasing. Okay. So, the curve 1 minus beta is called the power curve, okay, and you can plot 1 minus beta as a function of, let us say, mu naught, and if let us say this was your value of mu naught corresponding to h naught is true, and you plot your 1 minus beta curve, it will look something like this, where far from it you will get a value which is close to 1, okay, which is close to 1. Why? Because when mu is far from this value, then you will never, it is unlikely that you will make this mistake. Okay, your beta will 0. If your curves are shifted, are separated from each other, okay, if your curves are separated from each other, then you will get a value of beta which is equal to 0, okay, and then 1 minus beta will approach 1. So, at two endpoints, this 1 minus beta curve approaches 1. Okay. So, we had discussed one more case for the case of binomial proportions. Okay. In this case, the standard error is given by root is equal to root of pq by n. Okay. But if we want to compare the means, okay, if you want to compare two binomial proportions, okay, how would we do it? So, in that case, let us say our null hypothesis. So, we want to compare the means of two binomial proportions. Okay. In this case, my h naught is going to be proportion p1 equal to p naught p2, and h a is going to be p1 not equal to p2. Okay. So, your test statistic z is calculated as p1 minus p2 by root of, so this is the experimental variable, by root of p hat q hat by n1 plus p2 hat q2 hat by n2. Okay. So, let us take a sample example to see how we can do this, solve this problem. Okay. So, imagine in hospital records of a given hospital, okay, suggest that 52 men out of 1000 and 23 women out of 1000 were admitted with heart disease, heart ailments. Okay. So, we want to know, is there, okay, a significant difference okay, in heart disease among men and women. Okay. So, what we want to calculate, so if I give you again this expression, okay. So, our H naught remains the same as before, that we want to calculate, we want to test the hypothesis whether P 1 is equal to P 2 or the alternate hypothesis P 1 is not equal to P 2. Okay. Now, we want to calculate this test statistic Z equal to P 1 hat minus P 2 hat by this. Okay. However, okay, we do not know, okay. So, we do not know what value of P to put for two different populations. Okay. So, what we can do is we can estimate P hat as an average. Okay. If we can estimate P hat, so you can have P 1 as x 1 by n 1 and P 2 as x 2 by n 2. Okay. You can put in the value of P hat as x 1 plus x 2 by n 1 plus n 2. Okay. And this will give you a value of 52 plus 23 by 1000 plus 1000, which is equal to 0.0375. Okay. So, based on this P hat value, I can calculate my Z. Okay. So, based on this P hat value, I can calculate my Z, which is, okay, P 1, which I know P 1 hat, which I know to be 0.052, okay, minus 0.023 by root of, I use this common value, okay, into Q, which is 0.9625 into 1 by 1000 plus 1 by 1000. So, if you plug in these values, you will get a value of 3.41. Okay. You will get a value of 3.41. Okay. So, for 95% for alpha equal to 0.05, okay, we know for a two tail test, okay, this value is much greater. So, Z of alpha by 2 is equal to 1.96. Okay. So, I know that 3.41 is much greater than Z of alpha by 2. So, I can say that the incidence of heart ailments is higher, that is statistically significant, okay, in men. Okay. Okay. So, this brings us to our understanding of test of hypothesis for reasonably large samples. Okay. But what if you were handling much smaller samples? So, the entire test statistics Z equal to x bar minus mu by S by root n being a normal distribution is only valid for large sample sizes. Okay. Okay. For large sample sizes. Okay. Imagine the following scenarios. Okay. You want to do some experiments in an animal model. So, what is your constraint? The constraint is to minimize killing of animals. Okay. Another example is, say for example, you want to characterize the diamond weight. some diamond characterization. Okay. So, because diamond is expensive, you cannot afford to take a large sample size. So, you are constrained to take a much smaller sample size, because of which your normal distribution assumption may not be valid. Okay. So, this question has been addressed. Okay. So, this question has been addressed by Gossett. Okay. Okay. And so, he published this study using, he defined T as x bar minus mu by S by root n, okay, and the distribution he obtained. So, he calculated this T by repeatedly, so by drawing repeated samples, okay, and computing T value. Okay. And he published this work under the pen name Student. Okay. So, this is why this particular test is called the Student's T tests. Okay. How does the T distribution look like? Okay. So, if your normal distribution is like this, okay, the T, okay, the T distribution is much flatter. Okay. Okay. So, the T distribution is also symmetric. So, this is your T and this is your normal. Okay. So, what you can see for the T distribution, this is also symmetric. Okay. So, this is symmetric, but it is more flatter. Okay. With heavier tails. What do we mean by heavier tails? You see, in this portion of the curve, these probabilities are higher, and at the peak it is much suppressed. So, this curve is on an average more flatter. Okay. And if you increase your sample size, or if as n tends to infinity, T distribution merges with the normal distribution. Okay. So, for large sample sizes, you will get the same value whether you use the T test or the normal test, normal distribution. Okay. So, for a T distribution, how do we do test of hypothesis? Okay. So, what is provided in a T table are the following. Okay. You have something called df, or the degrees of freedom, okay, and you have T of 0.1, T of 0.05, T of 0.025, T of 0.01, and again the degree of freedom. Okay. And the degrees of freedom has values 1, 2, 3, 4, okay, and you have these values provided. So on and so forth. So, df, or the degree of freedom, degrees of freedom, is nothing but n minus 1. So, if n is your sample size, okay, df is n minus 1. Okay. So, as in previous cases, okay, for the t distribution also you can calculate t of alpha, where alpha is the area under this curve. Okay. So, for example, okay, if n equal to 10, okay, if a sample, so n equal to 10 items has been chosen from a normal distribution, how will we find the value of t? Of t such that 1% of all values of t will be smaller. Okay. So, as per this question, what we are given is n equal to 10, okay, implying the degrees of freedom is equal to n minus 1 equal to 9. Okay. So, if I draw this distribution, okay, so 1%, so it corresponds to 0.01. Okay. So, I want to find the value corresponding to, okay, so I want to find the value corresponding to this particular value of t, okay, for n equal to, for df equal to 9. Okay. So, I can, as we have plotted, okay, for corresponding to 0.01 and df equal to, let us say 9, we find out what is the value of t. Okay. So, since we need t to be smaller for all these other values, so let us say this t value, okay, t of alpha, let us say comes out to be 2.8. So, implying since all our other values have to be smaller than t, then t has to be less than minus 2.821. Okay. So, that is how you would do it. Let us solve a sample example. Okay. So, a new process for producing, okay, synthetic diamonds can be profitable if average weight, okay, is greater than 0.5 carat. Now, you have taken n equal to 6 samples and their weights are respectively 0.46, 0.61, 0.52, 0.48, 0.57 and 0.54. So, you want to know, so based on this, is the average weight greater than 0.5 carat. Okay. So, how will you solve this problem? You begin with your null hypothesis, which is mu equal to 5. Your alternate hypothesis, mu is equal to 0.5, is mu is greater than 0.5. Okay. So, for these values I can calculate x bar to be 0.53 and I can calculate the standard deviation, okay, which will turn out to be 0.056. Okay. With these values of x bar and s, I can calculate the t statistic, which is x bar minus mu naught by s by root n. Okay. 0.53 minus 0.5 by 0.055 n by root of 6, okay, and I get a value of 1.32. Okay. Now, corresponding, so if I were to use I were to use alpha equal to 0.05, okay, and corresponding to df equal to n minus 1 equal to 5, I can calculate I can look up the t table to know that t at 0.05 is 2.015. Okay. So, if I were to draw this, okay, corresponding to this you have t as 2.015. Okay. But our calculated t, okay, so t is less than t of 0.05, right, t is less than this t value we have calculated to be 1.32, t is less than 0.05. So, I can conclude that H naught cannot be rejected as evidence is insufficient. Okay. You can calculate the 95% lower confidence interval, one sided confidence interval, okay, level. This comes out to be x bar minus t of 0.05 into s by root n, okay, which is 0.484, sorry, t of corresponding to this value of t, sorry, t into s by root n, okay. So, 0.25 only, okay, you calculate to 0.84. So, this tells us that mu is greater than 0.484, but we want our assertion was mu is greater than 0.5. So, this is not true, because even a value of 0.5, 0.49 is not greater than 0.5. With that, I conclude our session for today. In the next class, we will begin with some little more discussion on t test and then go into chi-square distribution. Thank you for your attention.